So yeah, today we're going to do we're going to bound an extremal number, and we're going to actually use, basically we're going to show how you can sometimes use like supersaturation type things to prove extremal results. So just a definition, the d-dimensional hypercube is the graph with vertex set 0, 1 to the d, meaning all binary sequences of length d, where two vertices are adjacent if they differ in exactly one coordinate. So, for example, the one-dimensional cube, or one-dimensional hypercube, you've just got two vertices. One is labeled 0, one is labeled 1. So it's just a complete graph on two vertices. The two-dimensional cube is going to have four vertices, because it's, two, the size of the vertex set, right, is 2 squared. Your vertices are like 0, 0, 1, 0, 0, 1, 1, 1. I'm just going to write it by concatenating the symbols rather than, writing it as vectors or something. It's just like this. And then like 0, 0, these two are adjacent because they differ in the first coordinate. These two differ in the second coordinate. And that's kind of how it looks. Q3, give myself more space. So I mean, the reason this is called a hypercube is because it kind of generalizes a cube, right? So the three-dimensional hypercube is just a cube. We got 1, 0, 0, 0, 1, 0, 0, 0, 1. This will be 1, 1, 0, 1, 0, 1, 0, 1, 1, and then 1, 1, 1. Right. Okay, so so this is the three-dimensional cube. What we're going to prove today is an upper bound on the extremal number of this three-dimensional cube. So this is due to Erdős and Simonovitz from sometime, I think, in the 1980s. And so what they proved is that the extremal number of Q3 is big O of n to the 8 over 5. Or, in other words, n to the 1.6. So, I mean, most of the things we've been doing, like most of the things we've proved are either tight or very close to tight, or at least are conjectured to be tight. In this case, it's a little bit, the situation is less clear. So this will give us an upper bound of n to the 1.6, but we don't know if that's the right number. So in terms of lower bounds, So the best known lower bound, at least up to a constant factor or something, it just comes from the fact that, like, if you have a graph that doesn't have any C4s, then it won't have any cubes, right? Because the cube has 4 cycles in it. So so definitely the extremal number of the cube is at least the extremal number of the 4 cycle, which there's this example in the notes, so which if you've done assignment 3, then you've become familiar with it, right? So this is like n to the 3 over 2. But yeah, so we know it's at least kind of n to the 1.5, and it's at most n to the 1.6, but it's actually quite a major open problem to try to like sharpen either of these bounds, right? But yeah, let's prove this n to the 1.6. Maybe one thing first is to just notice that this doesn't like follow from the things we've done so far in any kind of trivial way. Like so far for bipartite graphs, we do have an upper bound already, but it's not as good as this. So let me kind of draw the 3-dimensional cube in another way. Ooh, interesting. Okay. So another way to represent the 3-dimensional hypercube is, so it's a bipartite graph with 4 vertices on each part, and it's basically like a complete bipartite graph, except I delete a perfect matching. So this vertex is adjacent to these 3. If you kind of check, well, actually we can even label the vertices, and it should be clear. So this would be like the vertex 0, 0, 0, 1, 1, 1. I think I'm doing this right, but so I guess all I'm saying here is that this is a subgraph of K4, 4. So we can say, kind of just using things we've already done, that this is at most the extremal number of K4, 4. But the bound we have on this isn't as good as that. So, so this is by the Turán theorem. This is big O of n to the, I think, 7 over 4. So it's like n to the 1.75. So we can already get a bound on this thing, but we want to improve that to like a 1.6 in the exponent. So yeah, this is by this I'm going to write it. I'm going to have to remember where all the accents are. But it's something like that anyway. Okay. So yeah, let's focus on proving this theorem. And I should say this proof is pretty relevant to the 4th assignment. So if you plan on doing the 4th assignment, then yeah, a lot of these ideas are going to be used there. Okay. So yeah, we're going to combine some things we've done, well, and also something very similar to something we've done, but it's not quite the same. So let me start by stating a lemma, which is actually one of the assignment questions, so I won't prove it. But the lemma says if G has n vertices and at least n to the 3/2 edges, then the number of injective homomorphisms, so we're kind of, when you have a homomorphism that's injective, it's really like a proper copy, right? So the number of injective homomorphisms from C4 to G is at least the number of edges of G to the power 4 over the number of vertices of G to the power 4, which is n, right? So over n to the 4. Okay. This is kind of similar to various things we've done. Like we proved something about the number of homomorphism, like the homomorphism density of C4 compared to the number of edges. But this is just like a little bit, it's asking for something a little bit different. You want actually injective homomorphisms. So you want real like copies of C4. And yeah, so this is one of the things you'll have to do in your assignment. But I should probably, I mean, maybe a little bit of a hint for the assignment, like you will be able to throw something away. Like there's maybe like a constant factor that you could get here, but you know, it's good enough to just have a constant factor of 1 for the purposes of applying this. So we're going to use this lemma. We're also going to use another thing we've talked about, but we technically didn't prove, but we're going to use it anyway. So remember we talked at some point about extremal numbers of even cycles. So Bondi and Simonovitz, you know, for the case of the 6th cycle, what they prove is that the extremal number of the 6th cycle is big O of n to the 4/3. Okay. Maybe just a hint about how this is relevant. Like why would I care about 6 cycles and 4 cycles? Okay, 4 cycles. I kind of feel like 4 cycles are natural. Like a cube is made up of a bunch of faces that like are 4 cycles, and somehow that should be useful. The 6 cycle thing, if I think about a cube, right? So that's my 3-dimensional cube. I'm sort of going to use this result to kind of find like this, like you've got a 6 cycle in the middle of the cube. So yeah, if we can find kind of like a 6 cycle where there's some vertex that kind of dominates like every second vertex on that cube, or on that 6 cycle, and another vertex that dominates every, the other vertices on that 6 cycle, this is going to be useful for finding the cube, right? So that's kind of the relevance of this result. Okay. So I guess, the way I want to structure this is, let's try to prove this. It's going to fail. But then once we see why it fails, we can see what we need to add to make it work. So let's try to prove this. And yeah, the word try here is important. It's not gonna quite work, but we'll see what we need in order to make it work. So let G have n vertices. So it's a graph with n vertices. And let's say c times, or maybe 2c times n to the 8 over 5 edges, where c is a constant that we can choose later, as big as we want. Where, yeah, we choose c later, as long as it doesn't depend on n. It's, you know, so just think of c as something big. So as a first step, there's no harm in doing something we've done before, which is take G and drop down to like a bipartite subgraph with at least half the edges. You're not going to, I mean, like G could have been bipartite to begin with, so you may as well drop to a bipartite subgraph, and it's going to kind of help a little bit. So let G prime be a subgraph, a bipartite subgraph. With at least half as many edges, so at least c times n to the 8 over 5 edges. Okay. And yeah, there's really no harm in that. We just lose half the edges and makes things a little bit simpler to deal with a bipartite graph. And G could have been bipartite from the beginning, so I mean, we haven't lost anything, really. Okay. So yeah, somehow I'd like to use this lemma, which it does apply because like the number of edges is something like n to the 1.6, which is definitely bigger. I mean, if n is big enough, like, yeah, this is definitely bigger than n to the 1.5, which is what you need for the for this lemma. So, so since, like, I mean, we may as well just let c be bigger than 1 or something. So this is bigger than n to the 3 over 2. G prime has at least the number of edges of G prime to the 4 over n to the 4 injective homomorphisms of C4. Or in other words, there's at least that many injective homomorphisms from C4 to G prime. Yeah, so that's just by this lemma, which, yeah, I'm not proving, but you're going to have to prove. Okay. So I've got a lot of 4 cycles. I can now do a sort of pigeonhole thing to say, okay, if I've got a lot of 4 cycles, then there must be an edge that's contained in a lot of 4 cycles. So if I just divide by the number of edges, so there must exist an edge UV well, so let's kind of write it like this. Like, imagine the 4 cycle is labeled 1, 2, 3, 4. So there's an edge UV such that the number of injective homomorphisms of C4 to G, where 1 maps to U and 2 maps to V, is at least, so I'm going to divide this by the number of edges of G prime, which just cancels one of them from the top. So it's number of edges of G prime cubed over n to the 4. Okay. In other words, if you've got a lot of force cycles, then there's some edge that's in a lot of force cycles. Is that clear? Or any questions about that? Yeah, so for every injective force, homomorphism of a force cycle, there's some vertex where 1 goes and 2 goes, and they must go to an edge. And so there's some edge that appears, at least that many times. Yeah?
Is it the number of injective homomorphisms from C4 to G or G prime?
Yeah, sorry, G prime. Yeah, thanks. Yeah. So we've kind of left G behind, right? We're just dealing in this bipartite world for now on. Okay. And let's kind of figure out what this number is. So So if I just plug in the lower bound I have on the number of edges of G prime, so that's like C cubed n to the, what is it, 8 over 5, so it becomes like 24 over 5. 4 is 20 over 5. So yeah, in total that gives me C cubed n to the 4/5. Okay, so here's my picture. I've got some edge UV. Now I want to think about what is this like, what are the number of force cycles containing UV? Like what does that really represent? The number of injective force cycles. I mean, if I suppose I look at the neighborhood of U, right? And maybe we should, well, okay. It's kind of like the neighborhood of U excluding V or something, but anyway, let's kind of look at the neighborhood of U and neighborhood of V. Well, this number of force cycles, it just basically counts, actually, let's really kind of exclude V from this and exclude U from this. So this is the set neighborhood of U except for V. And yeah, this number of force cycles that contain UV, it just counts edges from between these sets, right? Because for every like if there's an edge here, it makes a force cycle, and if there's every force cycle corresponds to an edge between those two sets. So what this tells us is that so kind of therefore the number of edges from the neighborhood of U, take away V, to the neighborhood of V, take away U, is at least this C cubed n to the 4/5. Because those edges are in one-to-one correspondence with the injective force cycles that include that edge. And what would be nice, so basically we're saying the edges are pretty dense between these sets. And now, if there's a lot of edges between these sets, like if there's enough edges, you should be able to find a 6 cycle between those sets. If I can do that, then I win, because if I can find a 6 cycle going between these neighborhoods, right? In fact, I end up with a cube, and I actually have an extra edge that I don't even need. So yeah, if you find a 6 cycle between those sets, what you found is a copy of this graph where, yeah, this one will dominate all of those. They're adjacent. Like this is U and V, right? And so we've actually found, so if there exists a 4 cycle or 6 cycle in the neighborhood of U minus V union neighborhood of V minus U, we get a cube, so a Q3. In fact, we get a Q3 with an extra edge that we don't even need. So maybe I'll call this Q3 plus. This is like a three-dimensional cube with an extra edge that keeps it bipartite. So like this is, yeah, this. So it's like take a cube and add like an edge from like 1, 1, 1 to 0, 0, 0 or something. So is it clear how that gives us the thing? Okay, so like we know there's a lot of edges here between these sets. That should be helpful for finding a 6 cycle unless these sets are really big themselves. So like I guess in a very ideal situation, so let's see. So if, for example, so like this is a graph where the number of edges is like n to the 8 over 5. So sort of the average degree is like n to the 3 over 5 because there's n vertices. So let's say if every, let's say vertex had degree, let's say at most, 10 to the 10 times c times n to the 3 over 5. This is just kind of an arbitrary number here. Then we'd be good actually, because then like the extremal number of a graph where the number of vertices is the degree of U plus the degree of V of C6 would be, so the degree of U and the degree of V are like at most this thing. So 2 times 10 to the 10 times C times n to the 3/5. Which by the Bondi-Simonovitz theorem, this would be at most some constant times whatever number I've got here to the power 4/3. So it's like 2 times 10 to the 10 times c times n to the 3/5, all to the power 4/3, which is at most like some kind of other constant. Well, that I can kind of control with c kind of. So constant times c to the 4/3 times n to the 4/5. And the relevance here is that this 4/5 is exactly the same number I got over there. Right. and the power on this C is less than what I got over there. So if C is big enough, then the number of edges in this thing, this neighborhood minus V, neighborhood of U minus V, neighborhood of V minus U is like large enough that we have to find a C6. So all I'm saying here is that this extreme, like if we knew that every vertex had degree at most 10 to the 10, or any number here really, times this C. C was like the constant we had in front of the number of edges in G. Anyway, if every vertex, if there weren't any extremely large degrees, then we would be happy, because we've got this many edges between the neighborhoods, and this number, if C is large enough, that number is larger than whatever this is. Right, because I've got the same power of N and a bigger power of C over there. Does that make sense? But we don't have this, this guarantee. I mean, all we knew about the graph is it has a lot of edges, but there could be vertices of very high degree, vertices of very low degree. You can't really guarantee that every vertex has like kind of small degree, or degree bounded by some constant times the average degree. But there's a lemma that allows us to do this, so sort of a technical lemma. So yeah, this is basically the whole proof, apart from establishing that we can take a subgraph which will satisfy like a constraint like this, that it's got like n to the 8 over 5 edges, and the maximum degree is like bounded in terms of the average degree. So let's state this technical lemma. Okay, so the lemma says for all delta greater than 0, and for all capital C bigger than 0, there exists an epsilon which depends on delta, and it actually doesn't depend on C. And there exists an n naught, which will depend on delta and C. And there exists a gamma, which depends on delta. Okay. So 5 quantifiers here, such that if G is a graph with n vertices, so n at least n naught vertices, and at least capital C times n to the 1 plus delta edges, then G has a subgraph G prime such that, so we're going to want 3 different conditions. But basically the idea is going to be we want G prime to also be like quite dense in the sense like it should also have kind of a lot of edges, where if we consider this a lot of edges. But it should also have the property that there aren't any very large degree vertices. And also we want G prime to have at least like some vertices. Like we don't want G prime to have 1 vertex or something. So in particular we can get that the number of vertices in G prime is at least n to the epsilon. So if we started with a very big graph G, G prime is also very big. It's smaller, but it's still, as n goes to infinity, it goes to infinity. G prime has at least C over 2 times the number of vertices of G prime to the 1 plus delta edges. Which means basically like if G had kind of a lot of edges like C times n to the 1 plus delta, G prime pretty much satisfies the same thing. Okay, we lose a factor of 2, but it's not a big deal, right? We can afford losing factors of 2. And every vertex of G prime has degree at most gamma times the number of edges of G prime over number of vertices of G prime. Okay. Which is kind of saying every vertex has degree at most some constant times the average degree of the graph, right? Because, yeah, if you had, on average, a vertex will have degree like, so if the sum of the degrees is 2 times the number of edges, so the average degree is 2 times the number of edges over number of vertices. So this is kind of like the average degree. There should be a 2 here, but then this is like times some big constant, where that constant kind of crucially only depends on delta. And so if my C is really large, like I can make my, in an application of this, you can make your C, like once you've fixed your delta, you fixed your gamma, like you can make your C large with respect to that. Okay, so maybe I should say how we apply this in this proof. So going back to the theorem about the cube, if we go back to the beginning, we should still, as we did before, we should go from G to a bipartite subgraph. So back to the cube. So at the start, like we did, we kind of went from G to a bipartite graph with half the edges at least. And then we should go from G prime to a G double prime by applying the technical lemma. So this G double prime is like the G prime in the technical lemma. With my delta is 3 over 5. C is just the C from the beginning of this proof, like, and so the hypothesis holds, right? Because G prime has at least C times n to the 1 plus delta edges and n vertices. Oh yeah, at the beginning of the proof, we should have probably let n be very, very large, bigger than some n naught. So then this G double prime will satisfy, so it has at least n to the epsilon vertices, where epsilon is some number that depends on delta, which in this case is just 3 over 5, so just some number. It has v of g prime, sorry, c over 2. So we've lost maybe a factor of 2. 1 plus delta edges, so that's 1 plus delta is 8 over 5. And every vertex has degree at most this gamma, which only depends on delta. Delta is just 3 over 5, so this is just a number. This could be, for all intents and purposes, this could just be 10 to the 10. I don't know. I mean, it's just a number. Yeah, times the number of edges in G prime over the number of vertices in G prime. And basically, if you put all of this together, you can get that, indeed, like, you're going to find this 6th cycle in the neighborhoods, and therefore you're going to find the cube. So then follow the proof as before, right? Except that we're now dealing with G double prime. So show that G double prime has a lot of 4 cycles. Therefore, there's an edge that's in a lot of 4 cycles. Therefore, if I take that edge, there's a lot of edges in the neighborhood of those 2 vertices. And having a lot of edges in the neighborhoods are not that big. They're only this big. And so you can find a 6th cycle in there. OK. I'm not so sure about whether doing the proof in this way, failing and then fixing it was a good idea, but anyway. Any questions about that? Yeah.
We don't know anything about it, right?
Yeah.
It is just a number, I know that, but it can be small or big. Does it matter? I kind of lost of how this epsilon can go into the other group and if it matters or not.
Yeah, that's a good question. So it doesn't matter too much. Actually, I should say this technical lemma, if you look in the notes, there is like a very, like I do give a very specific, not just an existence, but like a very specific number for all of these things. So we kind of do know what it is, but in some sense it doesn't matter what it is. Yeah, so this epsilon, it's generally going to be quite small compared, like if delta is small, it's going to make your epsilon quite small. But the important thing, I guess, is, like, for example, so the lemma we had about injective 4 cycles, it doesn't require n to be large or anything. So that one, so on G double prime, we're first going to apply this lemma about finding injective 4 cycles. That's going to be fine. We're then going to try to apply the Bondi-Simonovitz theorem to find 6 cycles in the neighborhood. And that's going to be fine too, because so that theorem requires n to be large, but if n is large, then n to the epsilon is going to be large. Like, so if we need for the Bondi-Simonovitz theorem, like the number of vertices to be bigger than 1 trillion, well, just pick n large enough so that the number of vertices in the neighborhoods will, so like it's kind of okay as long as like this actually does go to infinity as n goes to infinity. That's all we really need. Oh yeah, maybe I should say also that all of these bounds are relative to the number of vertices of G double prime. Oh, this should have been a double prime here. Double prime, sorry. all of these bounds are relative to the number of vertices that this graph has, not the original graph or anything like that. So yeah, for that reason, it kind of works out. Yeah. So generally, the epsilon is going to be small, but it's okay. Any other questions? I'll maybe spend a couple of minutes giving an idea about how to prove this technical lemma, but it is rather technical. So. But basically, for your assignment 4, there's a question which is essentially asking you to generalize what we've done today. But so you should basically use this technical lemma. You don't have to reprove it or anything. I mean, the proof is in the notes, so you can apply this in the assignment. So. So, frankly, I don't have that much intuition about this. Like, we've done a lot of things like this before where actually what we were usually doing before is you take a graph, you want to reduce to a subgraph that has a high minimum degree. And then that was kind of clear what you do. Delete the lowest degree vertex and just keep doing it. And that's going to make the minimum degree higher eventually or something. In this case, like, what we want to do is we want to reduce to a graph with a low maximum degree, not a high minimum degree. We want a graph with a low, we want to have a low maximum degree. I guess maybe that would suggest delete the high degree vertices. But somehow the analysis of that doesn't work as well. So here's the idea. So let P be a large constant. So this is going to be nowhere near a proof, but there is a proof in the notes. Depending on delta. And then what we're going to do is I'm going to partition the vertices into V0 up to VP. So each class has about the same size. So approximately n over p vertices. And what I want to do is put all the highest degree vertices in V0. So all the, so if you like, you could first order the vertices by degree, and then you could say, okay, V0 is the highest ones, and then the next highest, or whatever. But all I really care is that the highest degree vertices should all go here. Okay. But otherwise, this is just an arbitrary partition. Okay. So in particular, if there are any vertices whose degree is like way higher than the average, they're going to be in V0. Okay. What do I mean by way higher? That's a little bit vague, but yeah. Anyone who's got a super high degree, they're going to be in here. So kind of case 1, out of time basically. But if at most half the edges in the whole graph are incident with V0, so have an endpoint in V0, well, I just delete V0. I only lost half the edges. And that that allowed me to get rid of all the high degree vertices all in one go, right? Because all the high degree vertices are here. If I delete it and I only lose half the edges, good, do it. Otherwise, take some VI where V0, like the number of edges between V0 and VI is maximum. So maybe it's V0 and V1, for example. And then delete everything else. And just keep that pair. The kind of key observation here is that what this will do is it'll kind of densify your graph. And then you kind of repeat this process. The graph keeps getting denser, and there's some kind of a sort of delicate kind of thing that happens where it turns out this has to terminate at some point, and when it terminates, you just delete the V0 at that point, and it kind of all works out. But yeah, this is super vague, but like I said, it is in the notes.